Start sharing again. Share. Thanks, Courtney. So I wanted to talk about pi 0 of diff plus of S4. So diff plus of S4, this means the space of orientation preserving diffeomorphisms from S4, the 4-sphere, to itself. So I'm not going to go into what the topology is, but there's this thing called the C-infinity topology. There's a strong and a weak version, but they turn out to be the same when the spaces you're looking at are, that's just for smooth maps between manifolds. And if you fix one manifold and another, there's a good notion of the topology. There's two good notions of the topology on the space of smooth maps between them. They turn out to coincide when the manifolds are compact. The crucial thing about these topologies is that, so let's take, for me at least, let's take a 1-parameter family of diffeomorphisms in this space. So if it's a continuous map, a continuous path in the space of diffeomorphisms, with this proper topology, a continuous path actually is a smooth path. In other words, is smooth in the parameter t, the time parameter. That's so you worry sometimes about 1-parameter families of diffeomorphisms which only vary continuously but not smoothly in the time parameter, and that is not an issue here. So, or I'm interested in like homotopies between paths, and same situation. A homotopy between two paths actually is a smooth homotopy, smooth in all the homotopy parameters. And so if I were doing homeomorphisms of S4, that's the topological mapping class group. That's and in that case, that's trivial by, so just say pi 0 of the space of homeomorphisms of S4, orientation preserving. This is, I don't need that extra. This is 0 by Alexander's trick, which is a stupid trick. It's to cone everything bad to a point. And that's a trick that doesn't work well in the smooth category at all. And so I would like to say that very little is known about this. Selman Akbulut has a paper which claims that this is not 0 by Akbulut. And I'm just going to say that there was an earlier version of the paper that had a mistake in it. And I haven't looked at it carefully, but he's a smart guy, so it's quite possible he has a good proof now that this is not 0. But I'm not sure, so I'll remain a little agnostic about it. And so it's possible it's 0, in which case I'm talking about this whole thing is about a trivial group, but we don't know, and it's quite possible it's not trivial. Okay, so I'm going to...
Wait, I have a question.
Yes, please.
So this new paper, like, do you know if there's a consensus, if people seem to think it's right, or if people are
I've asked around
suspicious?
and haven't heard an answer. So I don't know if anyone else has heard anything. And I've started to look at it a little bit. It does seem like, he's addressed whatever problem there was in the past version, which was a sort of rail boundary problem, which is an easy mistake to make. So I don't know. So I should just leave it there. The other thing to know, though, is that the other background is that Watanabe had a really kind of dramatic paper last year in which he proved that pi I of diff plus, well, he didn't do diff plus of S4, he did sort of something similar for the 4-ball rail boundary, but it's the same issue really, is non-zero for various i's, for some particular I, some i's. Not, he didn't have I equals 0 for some reason. And so but this in particular, this disproved the Smale conjecture, which was that the diffeomorphisms of S4 should be roughly the same homotopy equivalent to Sorry, I really should put the 4 ball here because S4, that's actually not rel boundary. So that's the correct statement. It disproves what's called the Smale conjecture, which is that the diffeomorphism of the space of diffeomorphisms of a ball should be homotopy equivalent to the space of isometries of the ball, fixing the origin. In other words, SO, whatever. So that was pretty dramatic. I think that's generally, I haven't been fully refereed, but that's generally accepted to be correct. Hold on one second. Sorry, interrupting family. It's on the dinner table. Okay, we're at home. I'm not going to pretend I'm not at home. Okay, so rather than whisper weirdly. Okay, so let me try to set up so I'm trying to talk about this pi0 diff plus of S4, and what I'm going to do is tell you how it relates to various other homotopy groups of other spaces, and also give you some generators, some explicit generators for for possibly a subgroup of it, and but just to have a picture in your head, what is an element of pi0 diff plus of S4? It's a isotopy class of self-diffeomorphisms of the 4 sphere. So that's why I call this the smooth mapping class group. An element is a mapping class, namely an isotopy class of self-diffeomorphisms. And lots is known about the mapping class groups of surfaces, but very little about other manifolds, and certainly almost nothing. You'd think S4, how could it possibly have a non-trivial mapping class group, but maybe it does. Okay, so I want to draw like a diagram of various groups, which kind of summarizes where I'm going, and I'll try to tell you afterwards what all the things mean. Okay, so over here I'm going to have pi0 of diff plus S4. That's what we're interested in studying. I'm going to have a fundamental group, I'll call it pi1 of S infinity, and I'll tell you what that is. That'll be the good bulk of the time, is what does that mean? That there's going to be a surjective map from that onto here. It's a little bit, I'll tell you that it's a little bit of a cheat to call it a fundamental group of a space. It's really a direct limit of fundamental groups of spaces, which might be the same thing as a fundamental group of direct limits, but I don't really care. So there's going to be a surjective map. H stands for handles, S stands for spheres. These are going to be embeddings of disjoint unions. It's going to be the fundamental group of embeddings of disjoint unions of spheres in certain 4 manifolds. There's going to be, there's a natural subgroup of this here, which is just the kernel of this map. And there's going to be so I'm going to tell you about another pi1, which is basically coming from a subspace of this group S infinity, this space S infinity, which really for each infinity is going to be replaced with an actual number n when I actually work in examples. There's going to be an inclusion-induced map here. So the content here is that the inclusion-induced map from the pi1 of S0 to pi1 of S0 infinity to pi1 of the ordinary S infinity the image is in the kernel of this map. And it might be equal to the whole kernel. And then there's going to be a map pi1 of S. There's going to be another space S hat infinity. So one of the kind of themes is going to be that these two are maybe kind of, I'll make this more clear in a minute, but they're maybe complementary in a certain sense. So there's some nice geometry to be figured out in these two different, they're two different subspaces of the spaces of embeddings of spheres into a certain 4 manifold. Okay, sorry, this is all kind of, and then of course, if you just follow this arrow here to there, you get the image, which I'll just write that as, this is, I call this I. Maybe I should put a 0 there and a hat here. So this is just H infinity composed with I hat. And this, I'll just, this is just the image of that map. And of course, that's just a subset. It might possibly be equal, maybe. And okay, so that's all these groups. Now I'm going to, in terms of the second part, is the more explicit topological part, is that I'm going to show how to get some elements of this smooth mapping class group. And those certain isotopy class, certain well-defined isotopy classes of maps, I'll call them tau sub W. And these are, tau stands for twist. So these are certain twists that are some sort of four-dimensional analog of Dane twists. What is W? W is a pair, R comma S. It's what's called a Montesinos twin. And what it is both R and S are embeddings of the two sphere into S4. And they intersect, I'm just gonna draw a schematic here. They intersect transversely at 2 points. So that's what a Montesinos twin is. Two embedded two spheres in S4 which intersect transversely at 2 points. And then from this, I'll show, so that's a very explicit geometric object. From this, I'll show how to get a particular self-diffeomorphism of S4. And these will give you some elements in pi0 diff plus of S4. I'm going to then relate this particular subgroup, which might or might not be all of the mapping class group of S4, with so I claim that this subgroup is actually generated in a very nice way by the Dane twist, by these Montesinos twists along a certain, so I'm going to give you a certain list of specific Montesinos twins. So W of I is going to be a specific, for each natural number I, there's a specific Montesinos twin. I keep looking to the side while I'm writing, and I can move my tablet so I'm looking at you. W of I then is going to be, it's a particular, I'll draw pictures and I'll show you. It's actually the S, the second sphere is going to be the same, but the first sphere, the R's, change. Okay, so this doesn't tell you a super lot, except it gives you the structure of my talk. I want to tell you what these groups are, and tell you what this map is. I can explain those things clearly, and then I want to tell you what, how to get this twist from a Montesinos twin, tell you specifically what this list of twins is, and then you will have everything you need to do to understand the statement. Then I'll make some comments on the statement as to why, what you might do to possibly, so one thing is, could I show that, how might you show, if I can show equality here, then we have a complete set of generators for the mapping class group of S4. And then we could use that either to, we could look at, say, Salmons-Akbulut examples and relate them to this and maybe find a larger class of examples. We could also, if there's a mistake in his proof, we could possibly show that all of these are actually trivial, and that would give a proof that the mapping class group is trivial. And I'll show how, and thinking about this relates to thinking about spaces, loops of spheres inside four manifolds, loops of two spheres. Okay, any questions so far? There's not really much to ask a question about yet. All right. So let me start in on these spaces of spheres. So
the inclusion sign is in the wrong direction, right?
Which inclusions? Oh, yeah. Thank you. I always do, when I do things vertically, when I do those vertically.
Yeah, I know.
Let me make that. That's what you meant, right?
Yeah.
And then the question mark is around the equal sign.
Right.
As to whether they're equal. Okay, great. All right, and then maybe I'll be able to hint at some of the, I probably won't be able to hint at the techniques in the proof. So I can go a little faster now, I think, having set that up. First of all, this is a string of notation. So first of all, I want to think about the connected sum. So we're given some n. Natural number, maybe 0. Then the connected sum of n copies of S2 cross S2. That's a space, so S2 cross S2 is something you understand. You can remove balls and glue them together. If n is 0, I just mean the identity for the connect sum operation is always sphere, so that means S4. And except I want to decorate this a little bit. I want to put a little dagger here, and this just means punctured. That means you remove 1 point. And there's a reason for this puncture. It doesn't, it temporarily, it won't seem super important. And so I want to think of this, I'm going to assign a space Sn, which is the space of embeddings of the disjoint union of n S2s into this connected sum of n S2 cross S2s with a puncture. 1 point removed, just avoiding a point. If you've ever thought about mapping class groups of surfaces, you understand that removing a point actually can be very important. What it's really going to help me is to take this limit to the infinity, this pass to a limit, which I need to do this. Let me just draw a quick picture of how you think of this. So maybe I'm going to think of my schematic is S1 cross S1, but I think of that as S2 cross S2. And I'm going to think of, let's say, I'll draw this. That'll be, that's going to be like S2 cross a point, just so we can have a sense of which direction is, which factor is first and which factor is second. This is my schematic for point cross S2. And actually, we're going to come very quickly to want to think about S2 cross a different point as well. So this might be like S2 cross Q. Now that's just in S2 cross S2. Now if I want to take a picture my picture for this punctured one and how one includes in the next is, there's our little puncture. So this would be the connected sum of two S2 cross S2s, and I can sort of, by puncturing it, I want to think of there being a natural inclusion of this into connected sum of 3 of them and so forth. That's the role the puncture plays. And so, in particular, I want to think of this the space of embeddings as being a pointed space. So the base point is going to be, I'll just write it this way, the disjoint union of n copies of S2 cross a fixed point inside the connected sum of n S2 cross S2s. So in other words, that base point would be copies of this meridional one, or this and this and this. So that's a particular fixed embedding of spheres. And then I'm going to be interested in loops starting and ending at that base point. Okay, so that's that's the base point. And the crucial thing though is that there's a different base point for each n, of course. I should really subscript with an n, but notice that Sn rel its base point embeds into this Sn plus 1 rel its base point in the following sense. If I have a particular embedding of a disjoint union of, first of all, I bet any embedding of a disjoint union of n spheres inside the connected sum of n S2 cross S2s, I can extend it to a disjoint union of n plus 1 spheres where I make the last sphere be the standard base point, the standard red meridian. And so that's a way to embed Sn into Sn plus 1, and then you can see that it takes the base point to the base point. And so that gives you that's how you get these.
What if one of your embeddings, one of the spheres intersects the standard place?
Oh, you mean intersects the next standard place?
Yeah, like it has a
Well, it won't. It stays away from that puncture, and the connected sum, the way you put the extra one on. I mean this.
Oh, I see.
So here's your little puncture.
Sure. Oh yeah. Oh yeah. I get it now.
Got it?
Yep.
Okay. So you're always safe. You just put that extra one on, and we're good. Questions? Any other questions? So because of this, you can get the inclusion induced map from one to the other. You know, pi1 of S1. I'm going to suppress mention of base points now. Maps to pi1 of S2, etc. And so you can get a limiting pi group, which if I were willing to review my point set topology, I might be able to decide whether there's actually a limiting space or whether I'm just talking about groups. But it doesn't matter. All I care about is the groups. But we'll define various homomorphisms from group homomorphisms from pi1 of Sn to various things, and we need to know they commute with these inclusion maps in order to have all those be defined at the infinity level. I want to tell you, so if I scroll back up for a minute, so that's this here. I don't know if my pointer shows up so well. That's that. Now I want to tell you what this 0 means and this hat means. And they're two natural, I want to describe two natural subspaces of these spaces of embeddings. And so the S0n is, I'm going to say it's those, I'm going to write in words, those embeddings. So an element of Sn is an embedding of a disjoint union of n spheres. They're really indexed from sphere number 1 up to sphere number n. So an embedding such that the ith S2 in this disjoint union of n spheres intersects the jth S2 point cross S2. I'll do that in blue so you know what I'm talking about. Point cross S2 in the connected sum of n S2 cross S2s transversely delta ij times. In other words, here's each of the point cross S2s, and I've got this some random embedding of a bunch of S2s in there, and I'm requiring that each of those, so you know, something like that might, you know, it could do this and it could wander. Oh, that you can't see that color very well. Well, I don't want to, maybe I'll just undo it. I think you see what I'm saying. It should intersect the blues just like the reds do, except they may have moved around a bit. So that's a particular subset, subspace of the space of embeddings. That's sort of the trivial one in a sense. And then the S hat n is those embeddings which are disjoint from all the S2 cross Qs for various, you know, in all the summands. In other words, disjoint from all the copies of this green curve up here. So they, and so the point is to note the base point, which is this, the collection of red circles going all across, that's in both of these subspaces. And so it's not hard to see that the inclusions of these spaces into the big space commutes with the inclusions of Sn into Sn plus 1. So you get a nice diagram. You get, from this, you can get reasonable notions of pi1 of S0 infinity and pi1 of S hat infinity. And I'll just state it right now. So in other words, I mean, you might temporarily forget about the infinity, just fix a particular n, maybe even just fix n equals 1. And you're looking at, two spheres moving around in S2 cross S2, sorry. And you're looking at those that remain transverse through all time to the blue one. You're looking at those that remain disjoint from the green one at various times, and then you're looking at, or the big space is all of them. It is possible that, let me page here. It could be the case that pi1 of S infinity modulo the normal subgroup generated by pi1 of S0 infinity is actually equal to pi1 of S infinity. Or, you know what I mean? In other words, what I'm really saying is that it's possible that if you take some long loop of disjoint unions of spheres, you can break into a concatenation of loops where, from a short interval, you remain transverse to the group blue, and then the next interval you remain disjoint from the green, and then the next you remain transverse to the blue, and so forth. You alternate back and forth between these two properties. If that were true, I could actually prove this would imply that that vertical equality, which I highlighted in red, was true. In other words, that these tau sub w of i's generate all of pi 0 diff plus of S4. And this is actually what I thought I knew when I said I thought I knew more 6 months ago. I thought I knew this was true, and then much conversation ensued with Dave Gabay, and he turns out he could also prove some great things if this was true, but neither of us are sure it's true. And I should say that Hannah Schwartz has some ideas that may be able to show this is not true. In other words, maybe give explicit instructions to loops of spheres being able to be disentangled. Of course, it's also the added complication that things may not be equal until you pass to far enough out in this sequence of inclusions of spaces. May be able to show. So that's just lots of people are thinking about this because it turns out to be interesting for many reasons. Time. All right. Okay, so that tells you. Let me scroll back up. Any questions for anyone?
Yeah, I actually had a question, Dave.
Yeah.
So if you go up, I mean, the pictures you were drawing look like you're drawing cut systems of curves on surfaces. I mean, what if you just dropped this all down in dimension and thought about embeddings of cut systems on surfaces with these restrictions? I mean, have you thought about that at all, or did you skip past that case?
Well, I kind of skipped past it. I sort of forgot. I mean, I thought about it, but I think everything's really super trivial. I think all these groups, these fundamental groups, are trivial in those cases. I mean, you can't really, as soon as you're in genus bigger than 1, you don't have a lot of, up to homotopy, you don't have a lot of loops of circles. Right, it's hard, if you're in a genus 2 surface and you start with a meridian, you try and move it around, you're not doing handle slides or anything, right? You're just isotoping these things around. How are you gonna get back to where you started with that in any interesting way? That's rough. So I think this is not, I mean, the picture is helpful for understanding what the formulas say, but.
I see, so you're sticking with like the connected component of the base point when you're.
Oh, yes.
Okay.
That's also, yeah.
Oh, yeah.
As soon as we do pi 1 of this, I might as well just say I'm in the connected component.
Got it. Thank you.
I suppress the base point, but that's the only component I consider.
Hi, Dave. I have a trivial question. So to include this connected sum to a higher connected sum, so you have a base point chosen for each connected sum, right?
That's correct. I have a base. Oh, yeah. Well, I think of that's the puncture.
Yeah, that's a puncture. So, but eventually you want to, so when you consider this embedding space, you want to fill in the puncture because you're embedding, you're embedding into a non-puncture connected sum, right?
Oh, no, no, no. I actually think of the SN is actually the space of embeddings in the punctured space.
Oh,
Sorry,
okay.
there's
Yeah, sorry, yeah. So,
And so in S2, you have fixed the P and the Q.
yeah, and I fix a P and a Q in S2, just some point. Yeah.
Just some P and Q.
so you fix two mark points PQ and then also a puncture in the connected sum.
Yeah.
Okay, okay.
Okay. Okay. So now let me tell you what this H infinity is. I mean, okay. So one crucial, so hard work involved. One is to show that this map is surjective. I'm going to define this map H, which is I claim quite a natural map. The hard work is showing it's surjective, which is a kind of surf theory. And then the other hard work is showing that the subgroup of it has these nice generators. So let me, maybe even today I'll only, yeah, I don't want to rush, and I do want to stop in due time for them. So let me tell you about the H. Okay, so we get this map. Well, so what happens is the map for each n, you have a homomorphism Hn from pi1 of this space of embeddings of n disjoint n spheres and to connect some of S2 cross S2s to pi0 of diff plus of S4 for each n. And so for each n. So these are not going to be surjective for fixed n. This is where you have to pass through the limit. But these will commute with, this map will commute with all the inclusion-induced maps on Sn into Sn plus 1 and so forth. And then it's the limit that I claim is, which is basically just saying if you have enough spheres, you can get any. So what is this map? So here's how you do it. So given some, I'm going to give a whoops. Oh, sorry about that. What was that? Okay. Given some gamma in pi1 of Sn, oops. So remember so that means gamma itself for gamma of each, so T is in S1. I think of S1 as 0 to 1, mod 1 being glued to 0. And so gamma of T is a map from a disjoint union of n copies of S2 into the connected sum of n S2 cross S2s, punctured. But then here's where I ignore the puncture to actually do some geometry. I can think of that as a subspace of the connected sum of n S2 cross S2s. Okay, so so how do I use, so I claim that I can use such a loop of spheres, loop of n spheres, to produce a diffeomorphism of S4, well-defined up to isotopy by the homotopy class of this loop of spheres. And so what you do is you're going to build, so given this, you build a, I'm going to build a six manifold, a six-dimensional manifold, I'll call it. It's going to be a bundle. I'll call it Z. Maybe it's sub gamma, but I don't want to say that, over S1. And so and its fibers. So the fibers are going to be 5-dimensional. They're going to be cobordisms. I'll say Y sub T. So for each T in S1, I get this fiber, which is 5-dimensional. And those are cobordisms from the 4-sphere to some manifold, some smooth manifold X sub T, which depends upon T, but which is diffeomorphic to S4. So this diffeomorphism, the important thing is this is non-canonical. This is just. So let me show you. So the schematic is going to look something like this: a cylinder. So this whole thing is my 6-manifold Z. For any point T in the base S1, I have this 5-manifold Y sub T, and it itself is a cobordism from S4 at the bottom to some 4-manifold XT at the top. When I say it's S4, I mean it really is canonically identified with S4, and there's one extra feature, and such that Y sub 0, that's the, let's say, according right here, this is Y sub 0, is canonically diffeomorphic to integral across S4, which hence, therefore, the top X0, that's up here, X0 is canonically diffeomorphic to S4, canonical up to isotopy or something, but and so therefore the whole point is that the top of this, so the top of Z, so Z itself is a cobordism right this way. Where did I go? Did the wrong damn. So Z is a cobordism from S1 cross S4 on the bottom. Oh, I didn't say that. I guess that's an extra part of it. It's actually a trivial cobordism on the bottom to a particular to some. I'll write it this way: S1 cross with some monodromy. I'll write cross sub phi S4. That just means 0, 1 cross S4 with 1 cross S4 glued to 0 cross S4 by phi. And phi will depend upon the homotopy class of gamma up to isotopy. So this is the monodromy of the bundle. That's a 4. So the point is you build a bundle with a certain monodromy. And the monodromy is determined by the monodromy is determined by the sphere. So how do we do this? Finally, I'm almost ready to stop. So
the monodromy is the diffeomorphism we're after, right?
the monodromy is the diffeomorphism you get when you go around the top. So you start at X0, flow around, you get back to it, and you get some diffeomorphism. S4, X0 is canonically identified with S4. The other fibers are, depends on how you get there, how you identify with S4. And in particular, when you get back to where you started, you have some interesting diffeomorphism S4. And so the way you build this thing, and this idea,
Dave, can I ask a question? Just
yeah,
like lower dimensional.
yeah.
Like if you replaced S4 by a surface, can you is this something you could do in that case too, where you could construct all the magnet?
Not if so the coordinate Y0 is canonically a product, and so all the others Y sub T is a product for non-canonically a product. If you're doing this with a surface and you want the vertical slices to be a product, you're not going to get anything interesting. But if you can do a construction like this in lower dimensions, where you just have a different surface at the bottom and top, and you can express mapping class groups of surfaces in some interesting way this way.
Okay.
Okay, so basically what happened, so what you want to think is that these cobordisms, each one is built by attaching handles. So that's what the spheres are giving you, is handle attaching data. So Y sub T is going to be built by starting with 0, 1 cross S4. That's maybe this much up to here. And then you attach to it N, sort of, I'm going to say standard 5-dimensional 2 handles. What that means is that they are they're standard just means they're a 2 handle is attached along a circle. This is a circle in 1 cross S4. So that's just take some standard unknots, take N of them, don't let them move for all t, they're the same, okay? And so this, it turns out the boundary of that is, so the top boundary, boundary plus, this is a cobordism, is, can be canonically identified with the connect sum of n S2 cross S2s. So that's the little bit of 5-dimensional topology there, is when you do these, or 4-dimensional topology, when you do these surgeries, you get S2 cross S2s. And then I'm going to attach to that n 5-dimensional 3 handles. It's a good thing I planned on stopping at 340. And n 5-dimensional 3 handles attached, so a 3 handle is attached along a 2-sphere. And I'm suppressing framing issues. That's something that I claim that you can suppress it here. In 5-dimensional 3 handles along this map, gamma of t. Remember, gamma of t, for each t, gamma of t is an embedding of ns2s. Those are the attaching spheres for the 3 handles. And notice that the crucial thing is that the base point is when you map to S2 cross point, I think I call it, whichever one it is. It's the one that should be canceled. So the crucial thing is that the base point embedding, the base point embedding is the one that makes the 3 handles cancel the 2 handles. And then there's, so because the 3 handles cancel the 2 handles, that's why the cobordism at time 0 is a product. But then as you move around, they may not actually, that's because they're transverse. It's the standard canceling attachment for the 2 handle. And so, so the idea is you start with a n 2 handles and n canceling 3 handles. You don't move the 2 handles, but you let the 3 handles wander all around until they get back to where they started. Of course, at any given time, they could be isotoped back to canceling position, but they're not actually in canceling position at the intermediate times until you get back and they're in canceling position. And the miracle of this is that you might, in principle, you can produce potentially interesting bundles. And in non-simply connected cases, you can actually produce non-trivial bundles this way. We don't know if you can produce non-trivial bundles, but this is the way in which a loop of disjoint unions of spheres produces a bundle, which then produces this interesting monodromy. And the claim is that, you know, to get any particular self-diffeomorphism of S4, any isotopy class, you just need to do this with a high enough n. And the other claim is that if you add one extra, the commuting with the inclusion maps thing is basically this claim that if you add one extra 2 handle and an extra 3 handle, but the 3 handle doesn't move, then it cancels for all time. And so you get the same diffeomorphism up there. And I should stop now because I promised I would, and because it's a good time and people do want to go to this talk at 4. So next week I will give a much shorter review of this, and then tell you where the Montesinos twins come in and sort of give a rough outline of proof.
So H cobordism applies in these dimensions, right? I don't remember.
Well, you know, I'm mixing 4, 5, and 6 here, so I don't know which one you want.
Well, I mean, just for Z, right? It applies to Z, right?
Yes.
So you have your dualized handles, and you know it's trivial.
Well, I mean, Z. Okay, I haven't shown you what the handle decomposition. I've given each fiber as a handle decomposition. Z itself is more complicated to describe its handle decomposition. Also, Z is not simply connected. So
oh, okay.
that's cobordism. Z itself, because you got S1 cross S4.
Oh, yeah. I forgot. So YT is the one that you're attaching the handles along.
That's right. I'm building,
I see.
building a bundle of 5 dimensional. I'm really just doing 5-dimensional constructions. but doing it in a parameterized way. So, so this Watanabe, the background is that Watanabe does something like this, but over higher dimensional spheres to get, well, it's a little different what he does, but. Other questions? Good. Then, yeah, I'll try to start. Maybe I'll start next time with the Montesinos twins. So I'm going to stop sharing, and I'm going to.
Hey, Dave, have you ever
Yeah.
looked at this old work of Bonahan on cobordisms of automorphisms of surfaces? When Peter asked about a version of your picture where the sort of the top circle is a surface automorphism, and as you pointed out, the bottom you would want like to be S2 cross S1 or something,
Right.
where you cap it off to get that seems kind of like that setting, and he was able to sort of classify this bordism group of automorphisms.
I see. Yeah. So okay, maybe I mean, well,
Yeah,
a
can't
good
you
low
imagine
dimensional.
adding
Oh,
like starting with the surface, adding a pair of one like three-dimensional one and canceling 1-2 handles, and
What's that?
I think the canceling thing you're not going to get anywhere. But if you just imagine, start with the two sphere at the bottom, S2, and attach two three-dimensional one handles, and now have their feet wander around and come back to where they started. At the top, you'll get a genus 2 surface at each time. So you'll get a bundle of genus 2 surfaces. And I claim the monodromy of that bundle of genus 2 surfaces can be quite interesting. And it's given by how these feet move around. It's what's called a point pushing map. In precise, you can think of the feet of that two animals just being pushing around. And so.
But what if I started with, instead of an S2, a torus, and then I attached on like a handle, and then moved the feet of the handle and with a canceling two handle, like
I see.
and then move the feet of that around till it gets back. Like it seems like I should be able to get some interesting diffeomorphisms on the other side. Like
That's
Yeah,
possible.
I mean, I think this is just related to this general question of when a surface automorphism extends over a compression body, which is like related to this Cass and Gordon stuff about homotopy ribbon, fiber knots, and stuff like that. So the constructions we're talking about are all going to be sort of like compression body automorphisms that are inducing some interesting surface automorphism on the larger genus boundary component. But more generally, you could just ask whether you could sort of fill in a surface automorphism with a compression body automorphism like this.
Yeah, good question.
I mean, I wanted something of like the same genus. I don't understand why that doesn't give you something non-trivial in lower dimension. I mean, like it seems like.
Well, but you added a handle, right?
Yeah, so I go from genus 1, I add and I think about sort of T2 cross I, then I attach on a canceling pair of three-dimensional 1 and 2 handles, and then I move the feet of the one handle around the torus. Like I start with the torus, I added, and then that seems like if I move that around some loop, and then
Well, you're moving the two handle somehow at the same time. I mean,
right?
I think if you fix the negative boundary, then the automorphism on the positive boundary will be determined by it.
I see.
The surface automorphism is going to be determined by its extension over a compression body if the automorphism is like the identity on the other end.
Okay. Understood. I understand.
Yeah, it should be because it cancels for all time. For
Right.
all time, the two handle cancels the one handle.
Right, because you're also having the two handle to drag around.
I want to break because I think I do want to go to the next talk. Melissa, can you share the link again do you have the Zoom link for the algebra talk?
Sure. Do you want me to drop it into the Zoom chat or just email?
Well, let's just drop in this. I guess if we drop in this Zoom chat, it doesn't help us, does it? I guess it's in our email. Never mind. It's in our email. So
What happens if you try to join out of the Zoom meeting from a Zoom
from a Zoom meeting. No,
Probably.
but you can copy and paste it, right?
That's a good point. That's a good point. Yeah. Okay.
You can put it in the chat and
Bye,
then-
Rob.
All right.
Uh,
Thank you, Dave. I really appreciate being able to join.
Bye, everybody.
Bye, everyone.
See you, Jeff. And
See ya.
Bye, Rob.
um,